Okay, so let's learn about lumped capacitance. So if we want to learn about transient heat transfer, where we want to look how heat transfers in a material as a function of time, one of the models, and perhaps the simplest model we can use, is the lumped capacitance model. And what this says is, let's say for instance we have a sphere, is that basically the conduction, the heat transfer within the sphere is so much greater than any convective transport that the temperature inside is completely constant. So let's call that T. The heat transfer inside the solid is so great that it's a uniform temperature T. Now, generally, this is only going to be true if you have a material with a high thermal conductivity, and generally it should be pretty small as well. So if you have something like copper, which has a really high thermal conductivity, that could be an indicator that you're going to want to use lumped capacitance. Okay, so anyways, so now extrapolating, how can we solve this? So not doing derivations, the equation that we have for lumped capacitance says dimensionless temperature is going to be equal to the exponential of negative n, which we'll define in a second, times the Biot number, times this, well, here, I'll do this actually, times the Fourier number, okay? And let's define what these three terms are. So n, well, actually, let's do the Biot number and the Fourier number first. So the Biot number we know is the heat transfer coefficient times your dimensionless length over the thermal conductivity of your solid. And then tau is going to be alpha over your characteristic length squared times time. Okay, and then n is going to be a function of geometry. So for planar, and well, here, let's see, we have planar, we have, oh god, cylinder, and then let's say we have a sphere, and then this is going to be 1, 2, and 3. So that's just what we're going to use for our n value in those different cases. And then we should have, if we have a constrained thing, we should be able to solve for something we're looking for. Let me also define dimensionless temperature, which is going to be temperature at some time t minus the ambient temperature, all over initial temperature minus the ambient. So with this setup, this really should be enough to solve any of the lumped capacitance questions. So I made 3 examples for different geometries and different setups. But then if you know all this, if you know how to set it up, it should just become algebra, and the analytical solutions are very easy. So let's try some of these. So we have a plane. Actually, yeah, okay, we'll do this. We'll have a plane. Let's say it's all uniform temperature. Okay, and let's just go right ahead and solve it. So our lumped capacitance model is dimensionless temperature equals the exponential of negative n Biot number tau. Let's start defining stuff. Our dimensionless temperature is going to be T minus TA over T naught minus TA. And so for this problem, they want us to find the temperature after 10 seconds, and we're given a ton of values. So obviously, if you're going to be given a question like this, it's not going to be laid out as I laid it out, so you're going to have to be able to read and then find this. So this is a constrained problem. So if we have this amount of data, or this amount of information, we have a time, we can solve for the unconstrained one, which is going to be this temperature at time t equals 10 seconds. Anyways. Okay, so that's our dimensionless temperature, which is going to be T, which is what we're going to solve for. The ambient temperature is 400 degrees Kelvin. Initial temperature is 250 minus 400 again. N for a plane we know is 1. The Biot number is going to be HL over K, and I don't have a length of our material. We're going to say the length is 1 meter. Very great problems here. Okay. We're going to call it L1, so it's not actually going to change anything. I just made that up. 500 over, what's our K? 450, which is, I think that's the thermal conductivity of copper, or roughly. Okay, so our B out number is going to be 50 over 45. 1.1 continuous. Let's solve for our tau. Now, I should have given you one more definition at the beginning. So tau is alpha. It's alpha over your characteristic length squared times t. Alpha is equal to thermal conductivity over density times the heat capacity. So you're generally going to have to solve for this value as well. So this alpha is completely a function of like material properties like density, thermal conductivity, and specific heat. So you should be able to solve for it. And if you don't have the information to solve it, if it's like a homework problem or something, you can look those values up. So for something like copper, all three of those values are known. Anyways, let's solve for alpha now. Alpha is going to be equal to 450. I'm also omitting units. They're all in SI, so it's convenient. And CP is 400. Okay, let's go ahead and do that calculation. So in SI units, this comes out to be 1.25 e to the negative 4. Generally, these values are pretty small in SI units. Okay. Okay, where do we want to go here? Let's now solve tau. So tau is going to be alpha over characteristic. Let's just call this length squared. Length squared times time. We know this to be. We can just plug in what we know. So this will be 1 squared, which is 1, times 10 seconds. 10 seconds is the SI unit. So basically, it's just going to be our alpha times 10, which, of course, is 1.25 e to the negative 3, or 0.00125. So now we have n, we have our B out number, we have tau. Let's go ahead and solve this. So, well, actually, let's lay out the whole expression. T minus 400 all over 250 minus 400 equals the exponential of negative, our n is just 1, so I'm going to omit it. Negative 1.11, it's our B out number, times our tau, which is 0.00125. Okay, let's plug this into our calculator. So the two numbers in the exponential multiply together, e to that number. This is roughly equal to 1.0014, we'll call it. Actually, hold on. That was supposed to be negative. I was supposed to take the exponential of the negative of that number. Okay, there we go. So this becomes 0.3674 as well. Okay, and then let's times 250 minus 400 is negative 150, times by negative 150. Over the next problem. And then times by 150, you get t minus 400 equals negative 55. Add over 400. And then we're going to get t is equal to 344.9 seconds. For the I solved for temperature. Why did I call that seconds? This is degrees Kelvin. So let's intuitively think about this for a second. Initial temperature is 250, and there is contact at one surface where this outside is 400 degrees Kelvin. And after 10 seconds, which is a pretty short period of time, this 250 Kelvin is going to end up rising to 344.9. So seems like a reasonable solution. It's somewhere in between these two. All right, cylinder problem. find the heat transfer coefficient H if after 2 minutes or 120 seconds for SI, the cylinder temperature is 20 degrees Celsius, which we know is 293 degrees Kelvin. And we're given a lot of the same constants. So we have a cylinder, and said cylinder has an extremely high K value, which means we can use lumped capacitance. This is a sufficiently high. And then there's just fluid flowing around it, all around it, with this ambient temperature. And then they want us to find the heat transfer coefficient. So let's set up our lumped capacitance model. Dimensionless temperature equals the exponential of negative n Biot number tau. And then let's go ahead and solve all these values. For a cylinder, we know n equals 2. We know the Biot number is the heat transfer coefficient times the dimensionless length. Let's make that r, and we're going to keep it r. And then thermal conductivity of the solid. Let me zoom in a little bit. Okay. We don't have an h. We'll say the h is the last is. Wait, that's what we're solving for. Duh. Of course, we don't have an h. Okay, h times, and we're not given a radius either. We're given a cross-sectional area. So we got to solve for radius. So we know that the area of a cylinder, or of a circle, I guess, is pi r squared, and this equals 6.28 centimeters squared. So radius squared equals 6.28 divided by pi, which is 2 centimeters squared. And if we take the square root, our radius is going to be 1.414 centimeters. Equivalently, that is 0.01414 meters. Okay, so we got our radius. This is going to be, we're going to plug it in right here. And then our K value is 690. I'm going to omit units because they're all in SI, therefore I know it's fine. I'll do that division real quick. So our radius divided by 690 is a very small number. It's 2.05 e, that's an e to the negative 5. All right, we got Biot. Let's do our dimensionless temperature. So this is the temperature at time t, which they told us is 20 degrees Celsius or 293 Kelvin. We're going to subtract off our ambient, which is 350, all over initial, which is 150, minus ambient, 350. Throw that in the calculator, 293 minus 350, all over negative 200. And that gets you positive 0.285. And then, let's see, we got n. Let's get our tau. So tau, the Fourier number, we know is equal to alpha over a characteristic length squared, which we said was r times the time. Let's go ahead and let's calculate alpha first. Alpha is going to be, we know alpha is the thermal conductivity over the density times the specific heat. And we know all of these numbers for our material. If we didn't know them, we could look them up, probably. And let's make sure these are all in SI. Yep. And then what are we looking for? Specific heat. Yeah, those are all SI units. So if they're all in SI units, you can kind of just assume they cancel. That's good practice. I'm joking. Okay. Let me write this better. 6.8. We're forgetting. Yeah, actually, this is just alpha. 8.5. We'll call it e to the negative 4. All right. And then let's solve tau, which is going to be that in the numerator, our radius in the denominator squared, times time, which is 2 minutes or 120 seconds. So take our alpha times by 120, divide by 0.01414 squared, and we get a tau value of 410.8. All right, so we have tau. We got tau. We have a dimensionless temperature. We have an n. We can solve for B out, and then B out is, we said, was this. B out is a function of h. So let's go ahead and solve the B out number and then equate it to this right here. All right. So our dimensionless temperature, 0.285, equals the exponential of -2 is our n times, we'll just call it the B out number, times 410.8. Okay, let's take the natural log of 0.285. -1.26 equals -2, B out number 410.8. Divide those numbers over. Okay, and we get that the B out number is going to be equal to 0.00153, which is equal to, we solved previously, we solved that previously. That came from this analysis. So we basically, that's just R divided by K. And then we can go ahead and divide that number over. So I'm dividing 0.00153 by 2.05 e to the negative fifth. If we go ahead and throw if we throw that in our calculator, you get that, that's green. You get that H equals 74.6 watt per meter Kelvin. Did I get that unit right? That's what it is. There's a meter squared. That's what it is, right? Yeah, meter squared. Let me make sure I didn't get a parenthesis wrong there, because I might have. Okay, yeah, 74.6 for our heat transfer coefficient. So here for the cylinder, it's the same algebraic problem you've seen before, as it's always going to be for lumped capacitance. Only difference here is that for a sphere, n is going to be equal to 2. And then, of course, I switched it up so that you solve for the heat transfer coefficient instead of whatever we solved for last time, like temperature or something. Okay, final problem. You have a metal ball, find the temperature it takes for it to reach its melting temperature, and we're given we're given some values. A ball I would consider a sphere, and we know spheres have the n values of 3. Find the time it takes to reach its melting temperature, so that's going to be the final temperature. And they want time, and time is going to come from tau. So within the lumped capacitance equation, we're going to solve for tau. So in order to do that, if we know our n, we're going to need the dimensionless temperature, which is going to be, we know dimensionless temperature is the final time as a function of time, and then the ambient, that's an equal sign, minus the ambient over the initial minus the ambient, which is going to be, the final is the melting, which is 1,000, minus the ambient, which is 2,000, all over the initial, which is 150, minus the ambient, which is 2,000. Throw that into the calculator. You get 0.541. Let's go into the B out number. The B out number is the heat transfer coefficient times dimensionless length, which is R, or we'll call R over K. Let's see, we know H, we know K. We don't know R, but we do know a mass of the ball and then a density. so we can convert those into radius. So let's go ahead and do that. So first of all, we have 10 kilograms of ball. And if we flip the density, we have 1 meter cubed over 8,000 kilograms. And then the kilograms would cancel, and you just get a volume. So 10 divided by 8,000 is 0.00125 meter cubed. So that's our volume of our sphere. We know the volume of a sphere is 4/3 pi r cubed. So let's go ahead and solve for r. So take our result, times it by 3, divided by 4, divided by pi, take the 1/3 power, and then we're going to get a radius of 0.0668 meters. So now we can solve our BO number. H is 830, radius is 0.0668. K is known, 200. 830 times our radius, all over 200, is 0.2773. All right, now we have everything to go into our lumped capacitance and solve tau. So dimensionless temperature equals the exponential of negative n. Biot number, Fourier number, and in our case, this is going to be 0.541 equals the exponential of negative 3 times the Biot number, which we solved, times tau. Okay, let's take the natural log of that 0.541. Okay, there we go. Negative 0.615 equals negative 3 times the Biot number times tau. Divide over negative 3, divide over our Biot number. You get a Fourier number of 0.739. And we remember that this is defined as alpha over characteristic length squared. I'll call it r squared times time. Okay, and they want time, so we're going to need to solve for alpha, and then radius squares known. Our definition of alpha is going to be the thermal conductivity of your solid over its density times its specific heat. And we have all those values. So it's going to be 200 over 8,000 times 900. Actually, let me just write it once. 200 for K, and then 8,900. Okay. 8,900. Throw that in the calculator. And you get a alpha value of 0.278 e to the negative fifth. Sounds about right. Usually those are low. Let's go back to our tau. Tau equals, well, actually, let's just do this. 0.739 equals alpha, which we just solved, all over r squared, which we solved. Pre-r we said was 0.0688 squared. Okay, and then time. Let's go ahead and solve that. 0.0688 squared, and take 0.739 divided by what I just said, and then divide by the alpha value, and we get a t of a colossal number, 5620440. So what is that? 5 million seconds. If we put that into minutes, wait, let me put units, seconds. Equivalently 93,700 minutes. Let's divide it by, let's put it in hours. Holy shit, we're gonna have to go to days. Okay, we'll call it that many hours. Divide that by 24. Holy shit, it's 2 months. 65 days. All right, is that reasonable? Is a time of nearly 2 months reasonable? Let's read this. We have a ball. We have a ball that weighs 10 kilograms, and for us who don't know what a kilogram is, that's like 22 pounds or something, 23 pounds. Okay, so we have a 23-pound metal ball, and we want it to get up to 1,000 degrees Kelvin. Yeah, I guess you can't really intuitively think about this. It does have a high specific heat, though, so they take a lot of energy. So perhaps it's reasonable. And then so that's a quick walkthrough on 3 different geometries for using the lumped capacitance model. They're all connected by one simple algebraic equation, and you can solve for a bunch of different stuff, like you could solve for a length, you could solve for an H, or even a thermal conductivity through the B-out number. Thermal conductivity also shows up in tau through alpha. You can solve for times. That's probably going to be a common one. And then most commonly, you're going to solve for stuff in here, like a final temperature, an ambient temperature, an initial temperature, etc. And then the only difference between the geometries is that you are going to use these different n values. So that's the lumped capacitance model.